In this video, we'll talk about distance traveled and displacement, which are two important facts that come out of this idea of arc length and speed for parametric equations. How can we think about these concepts of distance traveled and displacement? So displacement is probably the easier one to think about. Displacement just says, where did I start, where did I end, and what is the distance between those 2 points that I got to over a certain time interval. My displacement over some interval is just where did I end minus where did I start, find the length of that straight line between those 2 points, and that will give my displacement. Distance traveled, on the other hand, is asking how much distance did I cover over this certain time interval? As in, how many steps did I take in my route to go from my starting point to my ending point? And an important fact to keep in mind here, displacement doesn't care about the actual route you took to get from point A to point B, just as you got from point A to point B. Distance traveled, however, actually cares about the route you take and how you actually get there to determine how much distance you traveled on this path. So as an example of this, if I have two different paths here, the purple path and an orange path, both of them have the same displacement because they both start and end at the same points. However, the purple one is a lot longer, and so it would have a longer distance traveled to get there. Distance traveled doesn't care which way you're moving, it adds up no matter what. Displacement, you get this sort of cancellation. If you go left, then go right, things will sort of cancel out as you go, and that will give you your displacement and not your distance traveled. So an important fact here is the idea of how fast are you moving and which does that factor into. So the speed of a parametric curve is given by just square root of x prime of t squared plus y prime of t squared, which you'll recognize as the integrand from our arc length formula. And that's not a coincidence because the length of the curve is the same thing as distance traveled, and adding up the speed at every point should give you distance traveled. The idea here is like an odometer in a car. Right? If I know how fast I'm going, my speedometer tells me how fast I'm going. If I sort of add that up in an appropriate way by scaling by delta t's, I'll get my distance traveled, which is what my odometer reads in the car. The odometer is distance traveled. Displacement is the straight line distance from where you started driving to where you ended driving. Those are two different things, and that's how we sort of set these up. In terms of doing actual calculations, we can get distance traveled or arc length by integrating speed. For displacement, we just have to find the starting point, the ending point, and find the distance between them. Let's do an example of what this might look like. So we'll have the path c of t, which is t squared e to the t. I want to find the speed at t equals 1, and then distance traveled and displacement over the interval between t equals 1 and t equals 3. So speed, which we have looked at before, is just the square root of x prime of t squared plus y prime of t squared, which in this case is square root of 2t squared plus e to the t squared. And so at t equals 1, the speed is the square root of 4, if I plug in 1 I get 2 squared, plus e squared. That's my speed at t equals 4. Now what about distance traveled and displacement over the interval from 1 to 3? So to get distance traveled, I need to integrate this speed function over that interval. So my distance traveled is the integral from 1 to 4 of the square root of 4t squared plus e to the 2t, which is my exact function for speed that I got above. And this integral you can't work out by hand, but you can do it numerically. And if you do that, you get a distance traveled of about 19.225. Now for displacement, you need to find the starting point and the ending point, and then find the straight line distance between those 2 points. So for displacement, I know that c of 3 is going to be the point 9e cubed, because if I plug in 3 to my equation, t squared e to the t, this is what I get. And c of 1 is going to be 1e, which means my displacement by the Pythagorean theorem is the square root of 9 minus 1 squared plus e cubed minus e squared, which is square root of 64 plus e cubed minus e squared. And if you work that one out, the number you get is about 19.121. So in this case, the values are both pretty close, but that's because my curve is always only going in one direction. T squared's only getting bigger, e to the t is only getting bigger. They're all going positive, so there's not any doubling back to make this a lot worse. However, we will see that the displacement is smaller than the distance traveled, and that's always the case. Right, that's the shortest distance between 2 points is a straight line. The only way that I get these two being equal is if I actually go on the straight line between the 2 points that I care about. Because this graph does curve a bit as it goes between C of 1 and C of 3, we're going to be slightly higher on the distance traveled than we are on the displacement. That's the idea of these two topics and how you compare them. The important thing being distance traveled is just adding up the speed. It's going to count all of my steps, whether they go left or right or double back or how they all work. Whereas displacement only cares about the start and the end points, and finding the length between those 2 points tell me how far I have net traveled over this time interval.